does day to day, what they focus on.
Right.
We're pulling insights from a pretty comprehensive resource, the Coating Inspector's Handbook by Tom Swan of MTest.
Well-known source, definitely.
So let's just jump right in.
Yeah.
What is the core role of a coating inspector? Because I think there's sometimes a bit of confusion there.
That's a perfect place to start, yeah. You know, lots of people in the industry, paint salesmen, engineers, maybe consultants, managers, even contractors, they might have some training.
They might know about it.
I guess. So their main job, their perspective, it's usually focused somewhere else. A dedicated coating inspector, they have a very specific primary role.
Okay, so strip away those other hats. Fundamentally, what are they there to do?
Simply put, they're there to verify that the quality of the work meets the project specifications.
Just the spec.
Well, the spec and industry standards for, good coding practices, they're the eyes on the ground, checking conformance.
Okay, verification. That immediately makes me think about the real world job site pressures.
Yeah.
Deadlines, budgets.
Exactly. That's the inherent conflict, isn't it? The push for quality versus the pressure to get it done fast and cheap.
Happens all the time.
It does. And while prioritizing quality almost always pays off long term, prevents those costly failures in the moment, even good contractors feel squeezed.
Yeah, the bottom line.
Right. And owners, too, sometimes they push to get a facility back online faster, maybe even against the advice of their own engineer or the inspector.
So that puts an inspector, maybe one working for the contractor doing QC, in a bit of a tough spot.
It really can. They have to take the measurements, record the work accurately, and sometimes, the contractor might wish those numbers looked a little different. Better, maybe.
Which just highlights that critical principle you hear all the time. If it is not documented, it didn't happen.
Oh, absolutely. That's the cornerstone. Your notes, your reports, sign forms, that's your record.
Your proof.
Your proof, exactly. It's your defense if something goes wrong later. Could end up in depositions, even court.
Wow.
So the inspector's job boils down to verify conformance to the spec and meticulously document everything.
What happens if the contractor doesn't have their own QC person on the job?
Well, then the inspector often ends up wearing both hats, quality control and quality assurance.
Double duty.
Yeah. And it significantly increases the workload. You're essentially checking things twice, maybe more, if work needs correction and reinspection.
I've also heard about inspectors sometimes getting asked to do more than just verify. Things like managing parts of the project, granting variances, even stopping the work.
That does happen, but you have to be really, really careful there.
Why is that?
Because with that extra authority comes way more responsibility and potential legal liability warranty issues. The whole 9 yards.
Right.
If you're not properly qualified or, crucially, don't have the right kind of liability insurance, taking on those roles is risky.
And the owner needs to be careful too.
Definitely. They shouldn't ask an inspector to make decisions outside their qualifications, like granting a variance from a design spec. That's usually an engineer's call. Certification shows training, not necessarily the authority to change the contract.
So it sounds like the inspector's work starts way before they even get to the job site. There's a whole prep phase.
Absolutely. Good inspection begins before you arrive. You need to understand what the owner actually needs.
Okay.
Assess the contractor's skill level. Have they done this specific type of work before? And then you really have to study all the contract documents, the coding systems being used.
So what kind of documents are we talking about? What's essential in that prep phase?
You need the whole package, basically, the specifications, and make sure you get all the addendums and appendices. That's where key details often hide.
Gotcha.
Applicable codes and standards, ASTM, NACE, ISO, whatever applies. The manufacturer's product data sheets, the PDS, that's like the technical roadmap for the paint.
Right, the instructions.
Exactly. Plus the MSDS, material safety data sheets for safety. Any manufacturer's application bulletins, they often have specific tips.
Okay.
And then the basics, drawings of the area and contact info for everyone involved, owner, engineer, contractor, paint salesman, technical service rep.
Getting everyone on the same page early seems key. That brings us to the pre-construction meeting. Sounds vital.
It is, but often coatings are just a small part of a big project.
Right. Gets lost in the shuffle.
Yeah, the coding discussion and the main pre-con meeting can get glossed over, treated as minor. So a separate meeting just for coatings, highly recommended.
Especially if your work isn't tied directly to other trades.
Exactly. If one isn't planned, you should ask for one.
And the main goal of that dedicated meeting?
It's your chance. Walk through the plans, the specs, resolve questions up front. Address any conflicts you found, like maybe the spec says one thing, the PDS says another. It happens.
Really? Often?
Surprisingly often, yeah. And hash out safety compliance stuff specific to the coatings. You want all this sorted before work starts, not when you're trying to paint.
And the contractor. They need to bring their own plan.
Yes, crucially, a written work plan. And it needs to be specific to this project, not some generic thing.
What should be in it?
Their QC plans, how they'll handle safety, environmental issues, and any areas where the spec gives them a choice, what choices they've made.
What's the big advantage of getting that from the contractor in writing?
Two main things. First, you can check it against the spec and PDS before work starts. Find those discrepancies early.
Okay.
Second, if disagreements pop up later on the job, you can often point back to the contractor's own written plan. Helps clarify things.
And if changes are agreed on during that meeting.
Get it in writing, absolutely. Distribute it to everyone who is there. Ideally, get signatures.
Protects everyone.
Exactly. Prevents arguments later about who said what.
Okay, so based on all that prep, the docs, the meeting, the contractor's plan, the inspector then develops their own inspection plan.
Right. It puts structure to your work, might have a general checklist, it's got all docs, standards, contact materials verified, stuff like that.
And then more detail.
Yeah, maybe an inspection summary sheet. Lists the critical things to check at each stage. Surface prep details, application parameters, the coating system itself products, temps, recoat times, DFT targets, pot life, cure times.
All the nuts and bolts.
And the specific inspection gear you'll need for each step.
And you mentioned the handbook has those QR codes. Handy for finding the equipment.
Yeah, they're at the end of sections. Quick link to find the tools just discussed. Pretty useful.
Okay, so moving on to the site work itself. You mentioned stages where work pauses for inspection. Hold points, right?
Yep, hold points. Critical stages where work stops, inspection happens before the next step starts. Mandatory check-ins, basically.
What are some standard ones you usually see?
They cover the whole process. There's one prior to the start of work. Checking the steel itself, sharp edges, welds okay, areas taped off right, checking the abrasive, the air supply.
Before any blasting starts.
Right. Then after surface preparation, checking for contamination, visual cleanliness. Did they meet the standard?
Okay.
Then immediately prior to application, checking climate conditions, temp, humidity, dew point, inspecting the paint materials again, watching them mix it.
Making sure they follow the PDS.
Exactly. Then following the application of each coat, checking wet film thickness, maybe holiday testing, watching recoat times, checking cure status.
And then the final one.
Yep, following the cure of the whole system. Final inspection, dry film thickness checks, final holiday testing if required, and then the sign-off.
And the project spec could add even more hold points.
Oh, yeah. Depending on how critical the job is or specific owner needs, they can add more checks at other stages.
Let's shift to reporting. The handbook stresses professional reports maintain credibility.
They're absolutely vital. Your reports verify the work, document everything. You can include drawings, photos if they help.
Do they have to be typed?
No, not necessarily. But they must be neat and legible. The handbook nails it. A report that cannot be read is the same as not having a report. It's useless.
Good point. If you find something wrong, a deficiency, how do you handle that in the report?
You note it clearly on the daily report for the day you found it. Then, crucially, when the contractor corrects it, you document the correction on a later report.
And link it back.
Yes, reference the original report where you first noted the problem, creates a clear paper trail, issue found, issue resolved.
Who gets these reports?
Typically, daily distribution to the contractor and the owner. It's also really useful to get the contractor to sign your report.
Sign it, meaning they agree with it.
Not necessarily agree with the content, just acknowledge they received it, like signing for a package or maybe a traffic ticket. It just shows receipt. This whole process, who gets reports, signing, that should all be discussed and agreed on in the pre-construction meeting. Documenting receipt protects both sides.
Speaking of the contractor, disagreements must happen sometimes.
Oh, they're pretty much inevitable. The key is how you handle them. Don't argue.
Easier said than done sometimes.
True. But try to listen, understand their point of view, restate their problem back to them as a question, make sure you've got it right.
What if it's about measurements? Like your DFT reading is different from theirs.
That's common. Suggest comparing instruments. Use the same calibration standard. Or measure the exact same spot together. Watch each other. Usually you can figure out if there's an instrument issue or a technique difference.
But what if you still can't agree?
Then you have to involve the owner. Remember, the contractor works for the owner.
Right.
Explain the situation clearly to the owner. Present your findings, your documentation. Explain the contractor's position too. Be fair. The owner makes the final call.
And what if the owner sides with the contractor, even if it goes against the spec?
It happens. If the owner says proceed, even though it doesn't meet the written spec, your job is to document.
What specifically?
Document the problem clearly. Document your findings showing it's out of spec. And critically, document that the owner reviewed it and gave approval to proceed without correction.
And in that specific case, you don't issue a non-conformance report.
Correct. Because the owner, who holds the contract, approved the deviation. So no NCR in that instance.
Okay, let's talk about NCRs, non-conformance reports. The handbook says these are serious business.
They absolutely are. An NCR is a formal flag saying something is significantly wrong and doesn't meet the contract. You only write one when absolutely necessary.
Why so serious?
Because they can have real consequences for the contractor, affect their ability to get future work, especially government jobs. It's a black mark.
So if you find something wrong and the contractor fixes it?
No NCR needed. You just document the deficiency and the correction in your daily reports. Problem solved.
When do you issue an NCR then?
When the contractor has gone past the point where the deficiency can be corrected to meet the spec. The classic example. The blast profile wasn't deep enough, but they've already put the primer on.
Too late to fix it.
Exactly. You can't re-blast through the primer. That's when an NCR is typically warranted.
Makes sense. Okay, before we dive into specific tests, maybe a quick rundown of the essential gear an inspector usually needs.
Sure. Having the right tools and making sure they work properly is fundamental. For most jobs, you'll need, let's see.
Environmental stuff for...
Right. A psychrometer could be a sling type or electronic for humidity and dew point. Thermometers for air and surface temps.
Then for the coating itself?
A wet film thickness gauge or WFT gauge. A dry film thickness gauge, DFT gauge, probably the most common tool people think of.
Surface prep.
Surface profile equipment that could be visual comparators, electronic profile gauges, or replica tape. Needs something to check that roughness. A holiday tester, if the spec requires checking for pinholes. Salt testing equipment for those invisible contaminants. A black light can be useful for finding oil. Blotter paper to check the air supply cleanliness.
Standards.
VIS standards, those photo guides for blast cleanliness. And a paint thermometer for the material temp.
Any optional extras?
Maybe a blast needle gauge or a nozzle orifice gauge to help troubleshoot blasting problems. And a camera invaluable for documentation these days.
And like we said, the QR codes in the handbook link to these tools.
Yep, handy feature.
Okay, let's get into the specifics, starting with environmental conditions, humidity and dew point. Why is measuring this so critical before painting?
This is huge. I mean, a massive number of coating failures trace right back to applying paint when the climate was wrong.
What are the typical limits?
Usually the spec will say something like, apply only when relative humidity is below 85%. And critically, the surface temperature must be at least 5 degrees Fahrenheit, that's about 3 Celsius, above the dew point.
The 5-degree spread.
Exactly. If you're working close to those limits, accuracy is absolutely essential. A small error can mean the difference between a good job and a failure waiting to happen.
Let's quickly define those terms. Dry bulb, wet bulb, dew point.
Okay. Dry bulb temperature, DBT, that's just the normal air temperature, measured in the shade.
Simple enough.
Wet bulb temperature, WBT, that's the temperature you get from a thermometer with its bulb covered by a wet wick with air moving over it. Evaporation causes cooling.
So it's usually lower than the dry bulb.
Right, unless the air is totally saturated, 100% humidity. The difference between dry bulb and wet bulb tells you how much moisture is in the air. Big difference means dry air, lots of evaporation. Small difference means humid air, less evaporation.
And dew point.
That's the temperature where the air becomes saturated and moisture will start to condense out onto surfaces. If your steel surface is at or below the dew point, you'll get condensation, invisible moisture.
Which acts like a contaminant.
Exactly. Paint won't stick properly.
Got it. So how do you measure these? The classic way is the sling psychrometer.
Yep, the manual method. Costs around $80 to $100 usually. First things first, check your thermometers. Red spirit ones are easier to read than mercury. Check for any breaks or separations in the liquid column.
Calibration.
You should do a quick field check. Make sure both thermometers read the same when they're dry and sitting in the shade. And check them in ice water should read 32 Fahrenheit, 0 Celsius. Note any difference, any offset.
Storage matters too.
Yeah, keep it in the shade. Don't let the instrument itself heat up. Check the wick on the wet bulb needs to be clean, white, flexible. Dirty wicks mess up evaporation. Use distilled water if you can. And make sure that wick is properly soaked. Water shouldn't beat up on it.
Okay, ready to sling. How do you do it?
You do it right there in the area you're going to paint. Face into the wind if possible. Rotate it steadily, about 2 revolutions per second for maybe 90 seconds.
Then read.
Read the wet bulb first. It changes faster. Then keep slinging for another 20-30 seconds. Take another wet bulb reading. Keep going until you get 2 consecutive wet bulb readings that are the same. That's your stable WBT.
How accurate is this whole sling method?
Well, check your dry bulb reading. Hasn't changed from before you started slinging. Accuracy really depends on the thermometer accuracy itself and your technique.
Errors can add up.
Oh, yeah. The handbook gives an example. Just a 1-degree error on each bulb in opposite directions can throw off your calculated RH and dew point quite a bit, especially near the limits.
And then you use charts or calculators.
Right. Psychrometric tables or an online calculator. The handbook mentions a NOAA link and even gives a spreadsheet formula. Those are generally more accurate than the old slide rules people used to use.
What about electronic meters for climate?
Generally, they're more accurate than the sling. And importantly, they minimize operator error. Different inspectors should get the same reading.
And data logging.
Big advantage. Many have field calibration options too. They create electronic records, often time and date stamped. Can transfer data to a computer. That's becoming standard, even required on lots of projects now. Even the cheaper electronic ones are often more accurate than a sling.
Okay, let's switch gears to surface preparation. The handbook calls this out, rightly, as a major cause of paint failures.
Yeah.
The main parts: profile and cleanliness. Let's tackle profile first.
Right, surface profile. Basically, it's the roughness, the texture of the surface after blasting.
How deep the peaks and valleys are.
Yeah, it's part of it. Depth, yes, but also how dense those peaks are and their shape. Are they rounded, like with shot, or sharp and angular, like with grit?
And why does that profile matter so much?
It's all about adhesion, how well the paint sticks. That profile creates a mechanical anchor for the paint.
Like tiny hooks.
Kind of, yeah. A rougher surface gives a better mechanical bond. Plus, it massively increases the actual surface area the paint can bond to. Different paints need different textures.
You mentioned peak density.
Yeah.
Seems important, but maybe overlooked.
It really is. Hugely important for the bond. You could have 2 surfaces with the same depth measurement, right?
Okay.
But one might have peaks far apart, low density. The other has peaks crammed together, high density. That high density surface gives way more points for the paint to grip.
Which abrasives give different densities?
Generally, sandblasting gives high density. Shot blasting, often lower density, more rounded peaks. Grit gives you that angular profile. Newer tools, like the Defelsco RTRP, are making it easier to measure density along with depth now.
Right. And you can't get one single exact depth number anyway. It varies. You aim for an average or max.
Exactly. Using standard methods. ASTM D4417 covers the main field methods. Method A is visual comparators, B is profile gauges, C is replica tape.
Let's look at Method A visual comparators.
These are like little swatches, metal or plastic, showing different profile ranges created by different media, sand, shot, grit. You hold it next to the blasted surface, use a magnifier, and compare visually.
Subjective, though.
Very subjective. Accuracy is maybe plus or minus half a mil, depends heavily on experience, and you need the right comparator for the abrasive used. Grit profiles can be especially tough to judge this way. No permanent record either. Best used to kind of calibrate your eye, maybe alongside other methods.
Okay. Method B, surface profile gauge, or profilometer.
These are usually digital now, like the Defelsco Positector SPG. They have a fine tip that measures down into the valleys.
Advantages.
Much more objective. They automate averaging, record data average, min, max. You can download it for a permanent record. Generally considered the most accurate, reliable field method. And often, you can take fewer readings than the old standards required for mechanical gauges, saving time.
And Method C, replica tape.
Yeah.
Like Testex tape.
Right. It's a special foam tape. You press it onto the blasted surface, rub it really hard. That's called burnishing to create an impression.
A physical copy of the profile.
Exactly. Then you measure the thickness of that compressed tape using a special micrometer.
Pros and cons of tape.
Pro. You get a permanent physical record you can measure later. It's easy to do in the field. Less operator subjectivity in the measurement part. A con can get costly if you need lots of tests. The burnishing step is absolutely critical. If you don't rub hard enough, your reading will be too low. And the micrometer reads the thickest part of the impression, so it's closer to the maximum peak height, not the average depth. Using a wrong grade of tape or measuring it repeatedly also gives bad results.
Tell me more about burnishing. How do you do it right?
It just means compacting that foam fully into the profile. ASTM doesn't specify the tool, but any hard, smooth object works. End of a pen, swizzle stick, edge of the tape dispenser. Key is firm, consistent pressure over the whole measurement area.
Can you measure old tape samples, say, weeks or months later?
Yeah, generally, once that foam is compressed, it holds the profile pretty well indefinitely, unless you, measure it over and over in the same spot or store heavy stuff on top of it.
What about surface roughness testers? Are they common in the field?
Not usually for routine field inspection, more of a lab tool, typically. They use a diamond stylus that scans the surface, recording detailed data peaks, valleys, frequency, density.
More sophisticated.
Yeah, and more expensive, starting around $1,200, $2,500 maybe. Downside is the stylus might be too big for the very bottom of sharp valleys, but they're great for getting accurate peak counts.
Okay, say you measure the profile and it's too high or too low compared to the spec. What could be causing that?
First, double check your measurement, using the right method. Instrument calibrated, technique, okay.
If the measurement seems right, then what?
Look at the blasting process itself. Air pressure at the nozzle, use a needle gauge to check it. Nozzle orifice size worn nozzles kill pressure and affect profile. Are they using the right abrasive type and size?
Media issues.
Could be. Is the media being over-recycled? Broken down grit doesn't cut as well? Run a sieve test on the media. Watch the operator pressure, standoff distance, angle all matter. Sometimes blasting over an existing profile can also give weird results.
And how does that profile affect the amount of paint needed?
Big impact on cost and coverage. A deeper profile means more surface area, more valleys to fill.
So you need more paint.
Significantly more paint just to fill that texture before you start building measurable thickness on the peaks. Rule of thumb. For every 10 mils of profile, you might need extra paint equal to about a 5 mil DFT coat. Maybe 0.5 times the profile depth.
Well, that's for smoother profiles.
Yeah, maybe 0.25 times for shot blast. This extra paint fills the valleys. It doesn't add to your DFT reading until you're above the peaks.
Which leads right into how profile affects DFT measurement itself.
Exactly. When you put a DFT gauge on that rough surface, it establishes a zero based on the steel's magnetic properties, but there's no flat zero line. The valleys are below that point.
And peaks are above it.
Right. The meter won't actually register paint thickness until the paint level gets above that instrument zero point, which is somewhere above the average peak height. This ties directly into the base metal reading, or BMR.
Okay, let's put profile aside for a moment. The other big part of surface prep, visual cleanliness.
Right. Along with profile, poor cleanliness, visible stuff like rust or scale, and invisible stuff like salts is a top cause of coating failures.
Visible cleanliness is about
How much mil-scale rust, old paint is removed, because paint just won't stick reliably to loose stuff.
And since you can't really measure this with a gauge, standards were developed.
Correct. SSPC, NACE, ISO. They have text standards describing the levels of cleanliness. And then visual standards, photo guides to help interpret the text, like SSPC, VIS1, VIS2, etc.
Can you give us a quick rundown of the main SSPC blast cleaning standards? SP5, SP10?
Sure. Before blasting, there's SSPC SP1 solvent cleaning. That's removing oil, grease, dirt, salts with solvents, or steam. Critical first step.
Then the blasting levels.
SSPC SP5 is white metal blast, the highest level, free of all visible contaminants, looks bright, uniform.
Okay.
SSPC SP10 is near white, almost as clean, but allows random staining on up to 5% of each unit area.
Unit area being?
Usually defined as about 9 square inches, 3 by 3.
Got it. Then SP6.
SSPC SP6 is commercial blast, allows more staining, up to 33% of each unit area, still removes all tightly adhering mil-scale, rust, paint.
And below that?
SSPC SP14 is industrial blast, allows tightly adhering mil-scale, rust, paint to remain on up to 10% of the area, and allows staining over the rest.
How does that differ from, say, a brush-off blast, SP7?
Different goals. SP7 brush-off is usually done to just roughen up an existing sound coating for repaint. You want to leave most of the old paint. SP14 industrial aims to remove most stuff, but accepts some tightly adhering material will stay.
And commercial versus industrial is basically the percentage allowed.
Yeah, the amount of staining and tightly adhering stuff allowed. 33% for commercial, 10% plus stains for industrial.
The handbook also mentions SSPC PA17. What's that?
That's a procedure standard. It tells you how to confirm the profile and peak count using the instruments from ASTM D4417, gives rules on frequency and location of measurements.
And critically, those VIS standards, the photo guides, they're just guides, right? Not the standard itself.
Absolutely crucial point. They are reference photos to help interpret the written standard. If there's a dispute, the text of the standard governs always.
Appearance can vary too.
Hugely. Depending on the abrasive used, you have to compare to the right photos in the guide based on the starting condition of the steel and the media used. The back of VIS-1 usually shows how different abrasives look even when they all meet SP5. They look different, but all pass based on the text description.
The handbook hits some common inspector questions, like the dull putty knife test. Is that for blasting?
No. That test applies after hand tool cleaning, SP2, or power tool cleaning, SP3. You scrape it to see if any loose stuff comes off. It checks the effectiveness of those methods, not blasting.
What if a contractor points to a picture in VSS1 and says, see, it looks like that?
You go back to the text. The picture is a guide. The text defines free of visible oil, grease, dust, etc. Use the right starting grade photos. Compare apples to apples regarding media.
And you definitely can't use VIS1 to judge surface profile.
Absolutely not. Cleanliness and profile are separate. If a spec says check profile using VIS1, that's just wrong. Needs clarification, maybe a consultant, before work starts.
When do you really need white metal, SP5, versus near white, SP10?
Generally, SP5 for the most critical stuff. Immersion service, metallizing, some inorganic zincs. SP10 is often fine for atmospheric exposure, but ultimately, the coating manufacturer makes the final call for their product in that service.
And on new steel.
Might be hard to tell the difference visually between SP5 and SP10 if there was no rust or scale to begin with.
What about achieving SP11? Power tool cleaning to bare metal with a profile.
That's tough. Requires specific tools. The handbook mentions the Monty Tower MBX bristle blaster as one tool often recommended for achieving that required 1 to 3.5 mil profile along with the visual cleanliness.
Okay, moving from visible dirt to the invisible stuff, salts. Handbook says this is also a primary failure cause.
Absolutely. Invisible contaminants, usually soluble salts like chlorides, sulfates, nitrates.
And they cause problems how? Two main ways.
Yeah. First, corrosion. Salts act as the electrolyte needed for the corrosion cell to work. Paint is supposed to block that.
And then the second way, osmotic blistering.
Exactly. It's like basic chemistry, nature-seeking equilibrium. If you trap a higher concentration of salt ions under the paint film than exists in the liquid outside the paint.
Like rainwater or condensation?
Right. Water will actually get pulled through the paint film to try and dilute the salt underneath. Paint acts like a semi-permeable membrane.
Water gets in, makes a blister.
Filled with salty water. Pressure builds up. Pop, blister. The handbook has a little diagram showing this water moving across the membrane towards the higher salt concentration. Even works at low concentrations, like a vapor phase reaction.
So the paint's permeability matters here.
Definitely. How easily water vapor can pass through it depends on the paint type, thickness, how well it's cured. Thicker, less permeable films resist it better.
The million-dollar question then, how much salt is too much?
Yeah. Rule of thumb. Less is better. Always. For atmospheric exposure where water doesn't pool, maybe you can tolerate a bit more.
But for immersion, tanks, pipes,
needs to be much cleaner. Ideally, the conductivity of contaminants under the paint should be significantly lower, like an order of magnitude lower, than the liquid outside. Pure water immersion needs basically undetectable salt levels. Potable water tanks often use a limit around 7 micrograms per square centimeter.
What if a spec gives limits in ppm, parts per million?
That's usually a red flag. ppm measures concentration in a liquid. A surface limit needs to be amount per area, like micrograms per square centimeter or milligrams per square meter, mgml.
So ppm in a spec is basically meaningless for a surface.
Pretty much, unless they also define the exact area tested and the volume of extraction water used, which they rarely do. If you see ppm for a surface limit, you have to go back to the spec writer or owner for clarification before starting. Don't guess.
Are salts and chlorides the same test?
Not quite. Chlorides, Cl, are one type of salt ion and a very common corrosive one. Chloride tests look specifically for that ion.
Okay.
Testing for total salts usually means measuring conductivity. It measures how well all dissolved ions conduct electricity in the extraction water. It's an indirect measure of total ionic contamination, measured in microsiemens per centimeter. Can you relate conductivity to TDS?
Roughly. You can estimate total dissolved solids, TDS and ppm, from conductivity using a conversion factor, often around 0.67. Roughly 1 ppm of sodium chloride gives about 2.2 as ionic conductivity.
So which is more critical to test for total salts or just chlorides?
Depends on the spec and the risk. Chlorides are bad actors for corrosion and blistering, but total salts drive osmotic blistering because it's about the total ion concentration difference.
So for immersion, total salts might be more relevant.
Often, yes, because blistering depends on that total concentration gradient across the film. For atmospheric exposure to rain, which is pure water, any significant trapped salt, chloride or otherwise, can potentially cause blistering. Specs with really low limits, like 3 diazotic GC rings, are being super cautious.
What are the best ways to test for these then? Depends if you need total salts, conductivity, or specific ions like chlorides chemistry.
For total salts conductivity.
Bresl patch method with a conductivity meter. Or the SCAT test kit, also read with a conductivity meter.
And for chloride specifically.
Kits like ChlorTest, or, again, using Bresl or SCAT extraction, but testing the water with chloride-specific methods like Quantabs or Kitagawa tubes. There are also kits like the CSN that test for chlorides, sulfates, and nitrates individually, but don't give a total salt reading.
And how much salt do these methods actually pull off the surface? Extraction efficiency.
Yeah, that varies. SCAT might only get around 25%. Bresl, if done well with good massaging, can get maybe 40% to 80%. It's important to run a blank test too. Check the patch and water for contamination.
Yeah, the other salt tests.
Potassium for cyanide paper. Quick check for active corrosion on steel right after blasting. Turns blue if ferrous ions are present. Doesn't quantify, not for other surfaces. Only Bresl has its own ISO standard right now.
What about finding oil or grease?
Blacklight inspection, ASTM A380. Uses UV light in the dark. Detects some oils and films. Doesn't work on all types, like mineral oils. 365 millimeter UV might work better than standard 450 millimeter blacklight sometimes.
Or the water trap test?
Simple but subjective. Water beads up on oil, spreads on clean steel, only really reliable for heavy contamination.
Okay, let's move on to testing the paint itself. Starting with wet film thickness, WFT.
Right, WFT. Measuring the paint thickness right after it goes on while it's wet.
Who does this usually?
Primarily a contractor QC check. Allows them to adjust their spray technique, gun settings, thinning before it dries. Inspectors should verify it, though. And
you can calculate the target WFT you're aiming for.
Yep. Simple formula. Target WFT, target DFT. Percent solids by volume. Or thinning, WFT equals DFT. 1+% thinner. Percent solids. Get the solids and thinner info from the PDS.
How do you use a WFT gauge? The cone type.
Yeah, the cone gauge is most common. Little metal or plastic notched gauge. You press it squarely into the wet paint, down to the substrate.
Then lift it out.
Lift it straight out. Look at the teeth. The WFT is between the highest numbered tooth that has wet paint on it and the next highest tooth that's clean. So if the 4 mil tooth is wet, but the 6 mil tooth is dry, your WFT is between 4 and 6 mils.
Any other types?
There's the fun gauge for clear coats like varnishes. Uses a lens pressed into the film. You measure the diameter of the mark left.
The handbook mentions mixing and thinning around here too. Why is that so critical?
Oh, huge cause of failures. Using the wrong thinner, wrong amount of thinner, wrong mix ratio for 2-part paints, not letting it induct or sit long enough after mixing, going past the pot life.
All can cause problems.
Big problems. Improper cure, poor adhesion, reduced life. You have to read and follow that PDS exactly. Record batch numbers, check dates too. Sometimes it's a bad batch from the factory. Even solvent evaporation rate matters too fast, can cause wrinkling or haze.
Okay, from wet to dry. Dry film thickness, DFT. Probably the most common inspection measurement.
Yeah, DFT. Measuring the thickness after the paint's cured. 2 main types of non-destructive gauges in the field. Type 1 mechanical banana gauges, magnetic pull-off, and Type 2 electronic gauges.
Which use?
Magnetic principle for steel, ferrous, or eddy current for non-ferrous like aluminum, or often dual probes that do both.
Pros and cons. Type 1 first.
Type 1, simple, durable, no batteries. Cons. Not as easy to calibrate, less accurate, maybe 5%, doesn't automatically zero to the substrate profile.
Type 2 electronic.
Pros, more accurate, in 93% typically, easier to calibrate and zero, can store readings, download data for reports. Big plus. Cons. Need batteries, more fragile, electronics can be sensitive.
Lots of standards cover DFT.
Yeah, ASTM, ISO. But a really common one referenced for steel structures, especially North America, is SSPC PA2.
Okay, let's unpack PA2. It gives a sampling plan, right? How many readings to take?
It does. For small areas, like up to 300 STU feet, it's 5-spot readings per 100 SWU feet. For larger areas, there's a formula for the number of test areas.
That's the formula.
It's basically 3 areas for the first 1,000 SQF plus 1 area for each additional 1,000 SQF or part thereof. So 3 plus total SF 1,000, 1,000.
Okay.
Then within each test area, you take 5 spot readings, and each spot reading is made up of 3 individual gauge readings.
So lots of readings on a big job.
Can be. Handbook example. 27,500 SQF needs 30 test areas, 150 spot readings, which means 450 individual gauge placements.
And clarify, a gauge reading is 1 touch, a spot reading is the average of 3.
Exactly. Gauge reading single probe touch. Spot reading or average of 3 gauge readings in about a 1-inch circle.
Now the PA2 acceptance criteria, this is crucial.
Absolutely vital. 2 parts. First, the average of all the spot readings over the whole job must be within the specified DFT range, min and max.
Okay, the overall average.
But second, and this catches people, each individual spot reading must be within a calculated range. No less than 80% of the specified minimum DFT and no more than 120% of the specified maximum DFT.
So individual spots have a wider tolerance.
Right, but individual gauge readings, they have no tolerance limit in PA2. It's all about the spot average. Example, SMEC is 12-15 mils. The PA2 range for any spot reading is 9.6 mils, 80% of 12 to 18.0 mils, 120% of 15.
How does the European standard ISO 19840 compare?
Different approach. Requires a minimum number of individual readings. Most should be at or above the nominal DFT.
All right.
No more than 20% can be below N, but none below 0.8 N, and all must be below the max. It also has an alternative plan using averages, a bit like PA2 spots.
If you need a Type 2 electronic meter, what features matter?
The Felsco Positector 6000 is popular for field use, robust, easy, decide. Integral probe or separate probe on a cable, more flexible.
Prototype.
Ferrous F for steel, non-ferrous NF for others, or dual FN for both. Memory's a big one. Standard holds maybe 250 readings. Advanced holds thousands in many batches. Huge time saver for big jobs, better reporting. Connectivity to Bluetooth USB.
How often do you verify calibration?
Manufacturer calibration is usually annual. Verification is what you do on site. Type 1, verify each use on known shims, subtract BMR. Type 2, PA2, says verify beginning and end of each shift using shims on the actual uncoated prepared substrate you're working on, and must 0 Type 2s on bare, non-ferrous substrates.
Let's circle back to BMR base metal reading. Handbook says it's misunderstood.
It really is, especially critical for thin coats. BMR is the reading you get on the bare, uncoated profiled substrate.
Affected by.
Steel's magnetic properties and the surface profile itself. The gauge establishes 0 based on the magnetic field. On a rough surface, that 0 is effectively averaged somewhere above the peaks.
So the values are below 0.
Exactly. The meter won't show any reading until the paint is thicker than that BMR offset. A Type 2 zeroed on the blast accounts for this. A Type 1 zeroed on a flat plate. You have to measure BMR on the blast and subtract it from your readings.
So why is getting DFT right so important anyway?
Well, first, contract says so. Owner paid for a certain thickness. Second, barrier protection generally. Thicker is better, up to a point.
Dangers of too thin or too thick.
Too thin. Might not cure properly if catalyzed, not enough barrier protection. Too thick. Can cause curing issues, solvent entrapment, internal stress leading to cracking, blistering. Need that Goldilocks thickness.
What if DFT's out of spec?
First call. Coating manufacturer's tech rep. Get their advice, preferably in writing, and don't argue over tenths of a mil.
Because of accuracy limits.
Yeah, meter accuracy, 3 through 5% BMR variations. PA2 allows 20% on spots anyway. Rounding helps nearest tenth for low DFT. Maybe nearest half mil above 2-3 mils is practical.
Can you measure DFT on concrete or wood, plastic?
Handbook says a definite maybe. It's possible, but trickier. Method is ultrasonics.
Like the Positector 200.
That's one example, yeah.
There.
Sends a sound pulse, times the echo from coating interfaces or the substrate.
What can it do?
Measure non-destructively on concrete, wood, plastic, composites. Advanced ones can measure multiple layers. Conforms to standards like ASTM D6132, ISO 2808, SSPC PA9.
Limitation.
Coating can't have aggregate, usually. Thickness limits, polyurea, for example, absorbs the sound signal. Substrate evenness is huge. Concrete variations can be bigger than the coating thickness.
What if readings are weird?
Could be false echoes. Use high H-low gates on the meter to filter signals outside the expected range. Take lots of readings, average them. Use coupe plant gel.
Okay, next test. Holiday testing.
Yeah.
Or porosity testing.
Right. Finding pinholes, voids, holidays that go all the way down to the substrate.
Requirements.
Coating must be non-conductive. Substrate must be conductive. Metal is best. Concrete is possible, but harder because its conductivity varies. There's also a newer UV method mentioned.
Which tester do you use? Low voltage or high voltage?
General rule, low voltage sponge tester for coatings up to about 20 mils on metal. High voltage spark tester for coatings over 20 mils on metal and for testing on concrete.
How do you set the voltage for high voltage if the spec doesn't say?
Check the PDS first. If nothing, rule of thumb is 100 volts per mil of DFT. Or use ANY's formulas. V525 hosts CT mils up to 30 mils, V1250 city above 30 mils.
Important warning, though.
Yes. High voltage testing can damage the coating if you use too much voltage or go too slow. Know what you're doing.
Let's talk low voltage first. Under 20 mils on metal.
Standards like ASTM D5162, SC's RP0188. Voltages vary. ASTM uses 67.5 V. ISO uses 9 V or 90 V. A tester where you can adjust voltage easily is handy.
Why use a wetting agent with this sponge?
Reduces water surface tension. Plain water can beat up and bridge right over a tiny pinhole without making contact. Wetting agent helps it flow into the hole.
Like photo flow.
Yeah, common choice. Avoid soap residue if recoating. You can often push sponge testing beyond 20 mils, maybe 30, 50 if the coating's not conductive.
Any tricks for tight spots?
Yeah. If you can't get the sponge in, sometimes you can use a wet finger from the hand holding the handle to probe. It'll still beep if you find one. Might feel a little zap on some units.
Can you use high voltage on thin films? Under 20 mils?
You can, but risk of damage is higher. SCRP0188 gives suggested lower voltages, like 1500 V for 811 mils. Use with caution.
High voltage procedure on metal.
Know your DFT first. Set the voltage correctly. Spec, PDS 100 V-mil or ANY's formula. Ground the tester firmly to the bare substrate. Pass the electrode brush spring over the surface systematically. Spark jumps at a holiday. Alarm sounds. Lots of standards cover the details.
High voltage on concrete. A whole different ball game.
Definitely more art than science. Concrete conductivity varies wildly. Grounding is key and tough.
How to ground.
Connect to rebar if possible and continuous. Bolted steel nearby. Drive rebar into wet ground next to slab. Wet sandbags over wire mesh on the concrete. Always check your circuit first touch electrode to bare concrete. Should get signal.
Setting the voltage on concrete.
Can't use steel settings, need higher voltage, and it might vary. Best way. Create test holidays, find minimum voltage needed to spark at different distances from ground. If voltage climbs further away, need higher test voltage or more ground points. Conductive primers make it much easier, like testing on metal.
Are these testers dangerous, the high voltage ones?
High voltage, yes, up to 40 kV plus surge, but low current DC pulse. Won't usually electrocute you like AC, but can give a nasty zap. Real danger is the startle reaction, falling, dropping stuff. Set sensitivity so it only alarms on a real spark.
And that UV holiday method.
Interesting idea. Some paints have UV fluorescent pigment. Shine the right UV light, black light or 365 millimeter. Holidays show as dark spots on bright paint or bright spots if over a UV primer. Need to know the right frequency.
Moving on to adhesion testing. 2 types. Tape, peel, and tensile. Both destructive. Yeah.
Yes, both are destructive. You damage the coating. Generally only done if there's a suspected problem or for specific QC checks.
Tape adhesion first. ASTM D3359, ISO 2409.
Right. Quick check if adhesion is generally adequate and designed for steel, maybe less consistent elsewhere. Not for measuring high adhesion levels, just checking if there's a basic bond.
When would you do it?
Suspect application issues, bad prep, missed overcoat window, checking old paint before recoating, failure analysis.
What tape to use? Permasil 99 is gone.
Yeah, history. Other tapes meet the spec now. Check M-Test website for examples. Key is using a standard compliant tape, agreed upon by everyone. It's more like drafting tape than duct tape. Note, ASTM and ISO specs call for slightly different tapes.
How accurate is it?
Not very precise numerically. Lots of variables affect it. Blade sharpness, dirt, coating elasticity, substrate, scoring technique, pull angle, pull speed, tape quality.
So the rating is simple?
Yeah, 0 to 5 scale based on % area removed. Avoids false precision. 5 is best, less than 5% removed. 0 is worst, over 65% or total removal.
How do you interpret a 3, say?
Depends. For a new system, you want 4 or 5. 0, 1, 2 usually mean problems. 3 is iffy, borderline. Check DFT. Too thick coatings can fail even with a good bond. Most important, where did it fail? Between coats, at the substrate, within the paint. Tape test is a tool, not a magic predictor.
Using it before overcoating old paint.
It's one factor. Good prep is still key. Test patch is wise. Ratings 3, 4, 5 might be okay if other things look good, but consult the supplier.
Single blade X-cut versus multi-blade crosshatch.
X-cut needs single blade, straight edge. Crosshatch is easier with multi-blade cutter. Ensure spacing, but needs flat surface. Check multi-blades on smoked glass. Single blade is cheaper.
Quick tips for tape testing.
Pull tape 180 degrees back on itself rapidly. Use sharp blades. Clean resurface before taping. Rub tape down well. Pull within 1-2 minutes. Run confirming tests. Keep the tape sample easier to read later. Report all details, ratings, failure mode, location, conditions. Keep standards handy.
Okay, finally, tensile adhesion. ASTM D4541, pulling dollies off.
Yep. Measures bond strength in psi, or cohesive strength of paint or substrate, also destructive, only when needed.
In the big warning, not all testers are equal.
Absolutely critical. The psi value you get depends hugely on the tester model. You cannot compare results from different types, like an alcometer 106 versus a PATTI, no valid conversion. ASTM recognizes 5 different types.
How do they compare, roughly?
Generally, type 2, like alcometer 106, gives lowest PSI. Type 3, HAT, alcometer 108, and some type 5 or higher. Type 4, PATTI, and other type 5, Defisco ATA, give highest values. PDS values are usually from PATTI tests.
What substrates work?
Need a firm substrate. Metal, concrete, stiff wood. Flexible stuff distorts the pull.
Bowling action matters.
Yeah.
Manual versus auto. Rate. Squareness.
Yes. Automatic testers, PATTI, Defisco ATM, generally give higher, more consistent results than manual ones due to controlled pull rate. Slow, steady, even pull is best. Squareness is vital. Need a direct perpendicular pull, no twisting. Some testers self-align better than others. Misalignment causes peel failure, not true tensile.
And rating the test. Just the psi isn't enough.
Definitely not. Record max psi and analyze the failure mode. Where did it break? Often more important than the number.
Failure modes again.
Adhesion between layers or paint to substrate. Cohesion within one paint layer. Glue failure, glue to paint, or glue to dolly invalid tests for coating adhesion. Record percentages of each mode, e.g. 750 psi, 30% adhesive substrate, 40% cohesive intermediate, 30% glue failure.
To score around the dolly or not.
Spec should say. ASTM is cautious scoring can cause cracks, lower psi. Not scoring might get influence from adjacent paint, higher psi. ISO requires scoring. General advice, don't score unless paint is very thick or rubbery. Discuss if spec is silent.
Which meter is best to buy?
Depends on spec requirements, budget, expected psi range. Alcometer 106 is cheapest, most common, but least accurate. PATTI, best pull, lab use. Hate good, portable.